Today's lecture is going to be about Newton's law of gravitation. This is the force that connects all objects with mass, in particular the planets and their orbits. So first off, we're going to identify gravity as the force that causes the orbits of the planets, okay? What makes the moon go around in a circle, okay? It's basically this force of gravity that causes the moon to go around a circle. Okay, we'll be able to calculate the magnitude of the gravitational force. We've already talked about the direction of this force because the direction is always going to be towards the center of the circle. We're going to also relate gravitational field strength to g, or gravitational acceleration, that we've been using up to now. And what happens when we have more than one object, okay? When I have an Earth and a moon, or multiple large planets, okay? And then we're going to finish with Kepler's three laws. So first off, gravity is a centripetal force, okay? Newton developed his three laws, and then he noticed that the moon goes in an orbit as well, okay? So the moon goes in a circle, so there must have been some force causing that moon to go in a circle, and that's where gravity comes in. Okay, so he thought about it, and he realizes the picture we have in the lower corner is from his Principia, where he came up with the force of gravity. And it started with a thought experiment where, he starts off on a high mountain and he shoots a cannonball, and we think of it as going in a parabola. Okay, but that's because we treat the Earth as generally flat. Okay, in short distances, it's close enough to flat that it works. Okay, as I shoot it farther and farther, however, I do need to take into account the fact that the Earth is not a flat surface. In fact, it's curved. And I shoot it faster and faster and faster, and at some point, I do reach a point where the curve of my projectile matches the curve of the Earth, and it just keeps going around and around until it hits me in the back of the head. Okay, in reality, this wouldn't work because I have air resistance, but it was just a thought experiment. Okay, so if projectiles can go in a circle like that, then the moon must go in a circle that way as well. So he came up with his Newton's law of universal gravitation, which is this formula that says the force of gravity, F sub g, is going to equal capital G, and capital G is a constant, okay? It's the universal gravitational constant. It has a value shown there of 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared, okay? But it's just a constant of proportionality, okay? I usually pronounce this formula as G times GMM over R squared. I do use an uppercase and a lowercase m. Sometimes it'll show up as an M1 or an M2. Okay, but the capital M I usually call the big mass. Okay, for the Earth and the Moon, the bigger one is the Earth. Lowercase m would be the smaller mass, which would be the Moon in this case. And r is the distance between the two masses, in particular the distance from the center of the Earth to the center of the Moon. Okay, it's important that you realize that r is calculated from the center of mass of the two objects, which for spheres is basically just the center of the object. Okay, multiplication is commutative, so it really doesn't matter which m is which object, but I like to keep it straight and say big M is the larger object. Okay, Newton actually did not find the gravitational constant G. G was later found by another person by the name of Lord Cavendish. Okay, and he's famous for finding G. But Newton basically said that the force, gravitational force, will be proportional to the product of the two masses, M1 times M2. And it would be inversely proportional to the square of the distance between the masses. Okay, so inversely proportional means a 1 over something type of relationship, and since it's proportional to the square, it's 1 over r squared. So in total, we just have this force of gravity is equal to GMM over r squared. This is a very important formula because we're going to see this formula again, not only in terms of gravitational forces, but also because of electrostatic forces, the force between two charged objects. Okay, Whenever I have an object with mass, okay, everything with mass creates an invisible gravitational field. It's not so much that it's invisible, but we um, basically model the area around it as being everything is attracted to that object. And that's what the level of attraction is called, the gravitational field. Okay, it's a vector, yes. We show it as a vector, and we add them as vectors, so we do need to be cognizant of that. Okay, so for the Earth, okay, all of the vectors, all of the gravitational fields for any mass point directly towards the object. Okay, so we see all these arrows in the picture, and they all point inwards towards the center of the Earth. Okay, and that arrow is important because if I take a mass and I put it next to the Earth, we know where it's going to fall. It's going to basically fall straight towards the Earth. Okay, so the direction is given there, and I'm going to talk about the magnitude. Okay, because the magnitude of the gravitational field is calculated by the definition. Okay, the definition of the gravitational field is basically defined as the gravitational force per unit mass. Basically, I want to define it as something that is mass independent. It doesn't matter if I put a 1 kilogram object there or a 1,000,000 kilogram object there. The gravitational field should be the same. So really all I do is I divide the force by little m. Okay, if I recall that capital F, okay, the gravitational field, force, remember capital F is equal to G capital M lowercase m over r squared. If I divide this by lowercase m, really all I'm doing is getting rid of the little m and ending up with this formula Gm over r squared. Okay, those of you who are paying attention will also notice that there's a minus sign in this equation. Okay, the minus sign, because my gravitational field is a vector, as was force, but my gravitational field in particular says the minus sign in this case indicates that it is towards the center of the Earth, not away. Okay, because if you think of it, the center of the Earth, it would be location 0. Everything else is away, so no matter what, if I'm pointing towards 0, it would be a negative vector. So that's really what that minus sign is saying. Okay, you can ignore the minus sign if you provide a direction instead. This G that we calculate, okay, that's given by capital G, 6.67 times 10 to the minus 11, capital M over r squared. These are basically, if I use the surface of the Earth and the mass of the Earth in this equation, okay, I will basically find that lowercase g is about 9.8 meters per second squared. Okay, or another form I could use it in is 9.8 newtons per kilogram. Those units are synonymous. Okay, and this is where we come up with that number 9.8. Yes, we derived it experimentally, but it also has a original calculation that comes from this Gm over r squared. Okay, and what it allows us to do is it allows us to calculate pretty much G anywhere, okay, not only on the surface of the Earth, but I can also calculate G somewhere out in space. So, for example, I'll let you do this at home. The radius of the Earth is approximately 6,400 kilometers. The mass of the Earth is roughly 6.0 times 10 to the 24 kilograms. So at home, what I'd like you to do is calculate the gravitational field strength at the surface of the Earth, and also calculate the gravitational field strength at the International Space Station, which has an altitude of about 350 kilometers. Okay, couple of points to be careful about while you're doing this at home. I'm giving you distances in kilometers. Okay, frequently we'll use kilometers, so you should double check. Since our distances are so big, it really doesn't make sense to use just meters. Okay, so you'll have to convert that. The second point is the fact that I said the distance is measured to the center of the objects. Okay, so the fact that I give you the altitude of the International Space Station, that altitude is measured from the surface of the Earth. You'll have to add the radius of the Earth in to calculate the distance from the space station to the center of the Earth. Okay, so do those calculations at home, and we'll talk about that the next day. So what happens, however, if I have more than one mass? Okay, in this case, both masses generate gravitational fields. Okay, and the net field strength at any point in space is going to be the vector sum. So I'm going to have an object here and an object here, and so if my gravitational field points towards them, okay, and if they were exactly the same object, right here in the middle, okay, right here in the middle, the left object is pulling to the left, the right object is pulling to the right, and my net gravitational field right in the middle turns out to be 0. Okay, for a larger object like the Earth and the Moon, okay, so if I have the Earth and then the Moon, the net gravitational field is 0, is a lot closer to the smaller object, okay, because the big Earth pulls a lot stronger than the little Moon. Okay, but somewhere right around there, they'll pull evenly, and I would find that there's a net gravitational field of 0. Okay, so here's another example. Okay, I have two different pictures, one where the Earth is between the Sun and the Moon, and another one where the Moon is between the Sun and the Earth. Okay, this is actually the position defined by spring tides, where the tides are going to be the greatest. Okay, remember the Moon, the reason we have tides is because the Moon attracts the water. Okay, the gravitational force, yes, even at that distance, the Moon can attract the water. And when the Sun and the Earth and the Moon all line up, the gravitational force from the Sun and the Moon combine, and we end up with larger tides than usual. Okay, so this is called spring tides. Okay, so in looking at this picture, where is the gravitational force on the Moon, on the Earth, going to be greatest? In the top picture or the bottom picture? Okay, it's going to be in the bottom picture, okay, because if I think of this, okay, on this picture, the Sun is pulling the Earth to the left, and the Moon is pulling the Earth to the right. The Sun's a lot bigger, but it's also a lot farther. The Moon's really close, but it's not really massive. But they're both pulling a little bit right and left, and the net gravitational field is not so big because one is positive and the other is negative. In this case, I have the Sun pulling to the left and the Moon pulling to the left as well. When I add those both of those up, they're both working in cooperation. Okay, so this is like, the Jonah and Namrata problem. Okay, the Moon and the Sun are both trying to pull me to one side, whereas in the other one, they're both fighting each other. Okay, so that brings us to Kepler's 3 laws. Okay, again, yes, there are 3 laws. There's always 3, it seems. Okay, there are 3 laws for Kepler. Newton has 3 laws. There are 3 laws of thermodynamics. And if you break the ideal gas law into Charles Boyle's and the Gay-Lussac, you also end up with 3 laws. It's just, there's just something magical about that number 3. Okay, if you have if you doubt that there's anything magical about the number 3, just remember Star Wars has 3 trilogies, so that's 3 times 3, and what more do you need? Okay, so Kepler's first law basically says that the orbits of the Moon and the planets are ellipses or elliptical. Okay, we're pretty much just going to focus on circles, but you do need to know that the orbit is an ellipse. Okay. And the thing about that ellipse is that the center planet, okay, or the central object, the Sun or the Earth in the case of the Moon, does not go in the center of the ellipse, okay? It is not an eye that looks like this, where that's the orbit and there's the Earth, okay? That's not how it works. Instead, the central object is at one of the foci, okay, either to one side, to the left, or over to the right. Okay, we'll talk about that a little bit in class because I have a great demonstration for it. And another thing to remember is that a circle is a trivial ellipse. Okay, it's a trivial ellipse in the same sense that a square is a rectangle. Okay, if I do one of those SAT analogy things, I don't think they actually do them anymore. But if you have a circle is to an ellipse as a square is to a rectangle. Okay, basically in a square, both sides are the same. In a circle, both axes are the same. Number 2, conservation of angular momentum. We don't really talk about angular momentum in this class, but if the formula works out that basically the velocity at a certain distance, v1 r1, is going to equal the velocity at any other distance, v2 r2. Okay, so even in ellipse, if I'm far away, it basically means my r is really big, but my v is really small. Okay, the way I usually end up describing it is that if you're closer, you're going faster. If you're farther away, you're going slower. So closer, faster, farther, slower. The third law is described as the law of periods. Okay, it's this complicated looking formula that's labeled as t squared over r cubed. Okay, it's basically the ratio of the period. Okay, t is called the period, or the amount of time it takes to make one full circle. Okay, r cubed is basically the radius of my circle for a circular orbit, and that's going to equal 4 pi squared over gm, where m is the central mass, not the orbiting mass. Okay, so it doesn't matter. So if I look at all the satellites orbiting the Earth, and I measure their period, t, and I measure their radius, r, it's going to be the same for those little satellites close to Earth as the space station, as satellites far from Earth, as the moon. Okay, if I measure their periods and radiuses and square the period divided by radius cubed, it will be the same. Okay, so just to look at the 3 laws in a little more detail, orbits are generally considered to be circles. Okay, Pluto and the comets will have more elliptical orbits. And the orbited mass sits at one of the foci of the ellipse. Okay, the foci of a circle is just the center of the circle. Kepler-2 looks actually kind of complicated. Okay, the way it's described is that the area of the ellipse that gets swept out by the orbiting object in a set amount of time is constant. Okay, so if all of these are the same amount of time t, the area turns out to be the same. That's a little too complicated for me. I don't really feel like doing the geometry and calculating the area of a sector of an ellipse. Okay, instead we talk about it as conservation of angular momentum, or v1 r1. Okay, so the v here and this distance, v1 r1, equals r2 v2, or pretty much faster, closer, faster, farther, slower. Okay, and so basically this is the formula we'll work with, v1 r1. I don't need the mass, it cancels from both sides, so that works. And Kepler-3, I don't really need you to remember that t squared over r cubed is going to equal 4 pi squared over gm. All I need you to remember is that it is some constant. Okay, some constant based on the mass of the central object and the gravitational constant, universal gravitational constant. Okay, otherwise it's just t squared over r cubed. If you want the full derivation, the problem with this formula, t squared over r cubed, is your calculators generally don't have a cubed button. Instead, you have to work with the y to the x. Not so hard when all you're doing is cubing something, but you also have to know how to take the cubed root of something. And we'll talk about that a little in class. So anyway, how do I come about with this complicated formula that says t squared over r cubed is equal to 4 pi squared over gm? Okay, it starts with 2 basic concepts. Okay, the first is gravitational force. Okay, that says the force of gravity is equal to gmm over r squared. And since the object is going in a circle, we do have to work with that assumption. Okay, the object going in a circle means I have the centripetal force. It's the only force acting on it. It's the net force, and so we have this force making me go in a circle. Or I can basically call it the orbiting mass, because that's the one going in a circle, times v squared over r, which is my centripetal acceleration. simplifying this by eliminating the two, by eliminating the r's that are the same and the orbiting mass, I get this formula that says g times the mass of the central object divided by r is equal to v squared. Okay, so if I can calculate v, great. Okay, and I can calculate v because I can basically measure what the circumference of my circle is. Okay, this is nothing more than circumference. Circumference. Awful spelling. Okay, and t is the period. Okay, remember I talked about that a little bit earlier. Okay, period is how much time it takes to make one full circle. So for the Earth going around the sun, it takes us exactly 1 year. Okay, for the moon, it takes us roughly 28 days for the moon to make one circle around the Earth. For us on the Earth, it takes us 24 hours to make one full circle. So that's what period is. Okay, it's basically like the second hand on the clock. Okay, and how much time does it take? So this is just circumference over period. And I can get velocity that way. So I'm going to make that substitution into my formula for velocity. So my formula now becomes gm over r is going to equal to the quantity 2 pi r over t squared. Okay. Squaring everything out, it becomes gm over r equals 4 pi squared r squared over t squared. Rearranging everything, I finally end up with this formula. You do not need to know the derivation this year, nor do you really need to know the 4 pi squared over gm. However, it's there if you want it. Okay? Thank you.